So today will be the last class for bipolar junction transistors. Um, so okay, so today will be the last class for bipolar junction transistors, and we will discuss whatever is left on heterojunction transistor. And from the next class, we'll move to MOS transistor. Right. So let me recap what we have done in the bipolar junction transistor. So we started with homojunction bipolar transistors. So homojunction means your base, emitter, and collector are all made of same semiconductor materials. In this case, it is silicon. We could have it in silicon or germanium, but silicon is preferred for homojunction transistors. Okay, and we discussed the uh, principle of operation and how to design this homojunction bipolar transistor. So if I recap the principle of operation, so let me take the forward active mode of operation, which is typically the common mode of operation. So here your base emitter junction is forward bias, collector base junction is reverse biased. So you have electron injection from emitter to base, right? And then the electrons diffuse. Then some of the electrons are combined in the base, and rest of the electrons are collected by the collector, right? So if you look at the current components, right? So if you look at the emitter, right? So emitter uh, has two components. So one is because of electrons and one is because of holes. So basically you could write down means IE is IN plus IP. So IN because of electron injection from N to P, and IP is because of hole injection from P to N, because your base emitter junction is forward biased. If you look at the base current, so base current has three components. So one is uh, your base current has three components. One is your IP, right? IP is the holes injected from P to N, then the recombination component in the base, and your ICO is the reverse current that I'm coming from the collector, right? Reverse saturation current. But assuming that in the normal operation, our collector base junction, even if it is reverse biased, but that it is not very highly reverse biased. So ICO is less than IP plus IBR. So mostly I call, means I write my base current is the whole component of the emitter current plus the recombination current, right? And collector current is ICN plus ICO, and it can be assumed means because ICN is the number of electrons collected by the collector, right? So I could write also means your ICN is IN minus IBR, right? So your ICN will be IN minus, right? I could also write right? Okay. So yeah, so we have already discussed this. So the goal means basically we have also derived the current components, and basically means this equation you know by now. So IN is Q Ni square emitter area dn type NB TB dash. So when I'm talking about Ni square, so here this Ni is nothing but Ni of base, right? Uh, because since we're talking about homojunction, that's fine. But when we're talking about IN, right? IN, this Ni here is the Ni of the base, right? So NIB square ADN, and we have NB TB dash. So TB dash is the neutral base region, width of the neutral base region TB dash. And since I also told you, because we do not have a uniform doping in the base, so your NB times TB dash is mostly defined by the Gummel number for the base, right? And GB is nothing but how your base doping varies uh, from 0 to TB dash, right? So if my NB is uniform, then it will be NB TB dash, right? But not necessarily that your NB is uniform, right? So this component will be there. This is the forward bias component, right? IEP similarly is depends on the Ni emitter. So Q Ni square AE dP by NET, and here also this Ne times Te is mostly written by the Gaumel number of the emitter, because emitter doping may not be uniform. So you could define that the Gaumel number here, right? Gaumel number for emitter is nothing but 0 to Te Nex times dx, right? So this is if you're given non-uniform means if you know how the doping varies, you could find the Gaumel number of Gaumel number for means emitter and the base, right? And IBR also you have derived. IBR will come in this form. So this is definitely an IB, right? Because this depends on the base charge. So Q NIB square 8 TB dash by 2 times NB tau n. So tau n is your recombination lifetime, right? So you are injecting electrons to the base. How much time it could stay without recombination? That is your tau n, right? And it also depends on the base doping. Okay. So what is important um, is your beta, right? So basically you want, I mean, basically whenever we talk about a bipolar junction transistor, right? So we want to have a higher beta, right? Beta is nothing but the current gain. Beta is common emitter current gain. We typically write down by IC by IB, and we want our beta to be high, right? Um, so so I could also write beta. So IC is nothing but your ICN, and IB I could write down this is IP plus IBR, right? The IP, the whole component in the emitter current plus IBR, right? And ICN is nothing but the transport factor times IN, because this I could write down IP, and IBR is nothing but 1 minus alpha T times IN, right? Right. Okay. So if I do this, so I could also write down like this: IN plus IP minus alpha T times IN, right? And if you divide, right? So I could do some math here, just make the life simpler. IN plus IP, and this will be my 1 minus alpha T IN plus IP, right? So if you look at this part, this is nothing but a emitter injection efficiency, right? So basically this is the ratio of the electron component of the emitter current divided by the total current. So this is your gamma, right? This is your emitter injection efficiency minus 1 by gamma alpha T, right? So if you look at your beta, right? So beta is nothing but gamma times alpha T, 1 minus gamma times alpha T, right? So you want your beta to be high, right? So if you want your beta to be high, then your gamma alpha T should approach 1, right? So gamma alpha T should approach 1. That means your gamma, when you're designing a bipolar junction transistor, you have to make sure that emitter injection efficiency is uh, is close to 1, and alpha T is close to 1. Alpha T is the base transport factor, right? If you look at alpha T is your base transport factor, and your gamma is the emitter injection efficiency, right? So since we want our gamma to be close to 1 and alpha T close to 1, this is how we design your bipolar junction transistor, right? And and if you see your gamma, it depends. Okay, so let me write down. So gamma is IN by IN plus IP, right? So to make sure that gamma is close to 1, we want our IP should approach 0, right? Right? Or we could write IP should be much less than IN, right? So this is the thing, right? So if you want our gamma to be very high, we want your IP, the whole component of the emitter current, should be much less than the electron component of the emitter current. right? So that's the reason. If you look at IP, means if I look at IP here, right? If I copy this part, so right, if you look at IP, right, right. So here, if you want to increase gamma, or if you want to reduce IP, so you have to increase your emitter doping, and you have to increase your emitter thickness, right, or thickness of the emitter and doping of the emitter, right? So basically, what you want, copy this. Okay. So you want your any to be your any to be high, right? Your T also to be high, right? And your NIE, you want it to be low, right? So so these are the things, right? So or if you want your DP also should be low, right? So these are the things you could do, right? So if you want to design a bipolar junction transistor for a low IP, then the only thing that you could do is you could increase your means emitter doping, which generally we do, and you increase your emitter thickness. So and emitter thickness, so to increase the emitter thickness, we go up to polyemitter, right? Because since we could not really um, increase your emitter thickness. Otherwise, your base will be far away from the surface, right? So you use the polysilicon, right? So you deposit polysilicon. Your emitter is mostly made of polysilicon, and since the polysilicon, I mean, emitter now, when you move to polyemitter, then you could deposit emitter, and deposition can be controlled. So you could go to any thickness as possible. And NIE, another thing is NIE. We have not yet discussed how to change NIE, but please keep in mind, right? So this is again a second order effect, right? So when you are, because you want your emitter to be very highly doped, right? Because emitter is generally highly doped. So when emitter is highly doped, so because you know that if the doping, if you go on increasing the doping at very high doping, your band gap also reduces, right? So you means your band gap reduces at very high doping, right? So if your band gap reduces at very high doping, your NI will increase, right? Right. So that will have a opposite effect on IP, because you are doping your emitter very high. If you're doping your emitter very high, your band gap is reducing. Since the band gap will be reducing, your NI will be affected, right? So to write down, so if your NE is high, your band gap will reduce. So that will again increase NI. NI increase means your IP will also increase, right? So this is a second order effect. I will call it the highly doped emitter effect, right? So highly doped emitters actually um, uh, increase the NI, right? Okay. What is, so this is how we do, right? And if you go to the base, right? So okay, so one thing is you have to reduce IP, right? That will increase gamma. To increase the transport factor, right? To increase that, so you also want your base transport factor to be very close to one, right? If you want your base transport factor very close to one, that means um, you want your alpha T close to one. That means your IBR, your recombination component, should approach towards zero, right? So if you want to have IBR to be zero, so only thing you could do is, because you do not want do not want recombination in the base, that means your tau n and the recombination lifetime the base should be high. So that you actually do by changing the defects, right? So the taking care of the defects in the base region. So defects need to be very low, right? Defects in the base region need to be very low. Also, your doping, the base doping, the higher the doping, there will be more recombination, right? So you want your base doping to be low, but you cannot you cannot really decrease your base doping. So base doping is medium, right? So basically, you cannot keep it very low. If you keep the base doping very low, anyway, recombination lifetime will increase. But your base doping cannot be very low. These are second order effect. So you keep it medium, right? And the TB, right? So base thickness, the neutral thickness, you need it to be low, right? See, the point is the moment. Uh, okay, so you are injecting electrons to the base and they're diffusing. So the quickly, so we want our electrons to reach the collector base junction very fast, right? And that depend on the doping gradient, and that also depend means the concentration gradient, so not doping gradient, concentration gradient, and it also depends on the base thickness, right? So we also derived that the transit time, right? TT, right? So transit time, right? So this is how much time the electrons spend in the base, right? This should be less than your recombination lifetime, right? So this is where we started, right? So we also discussed earlier, your transit time should be less than the recombination lifetime, right? Your TT should be less than tau n, right? So to have that, what you do actually is you um, reduce the base thickness, right? But when you reduce the base thickness, right? Let's say your base is here, right? And you, if you reduce the base thickness, so and you see, the point is, um, this is your TB dash, sorry, TB dash, and it has a doping NB, and you cannot have very low doping because low doping is preferred for the higher recombination lifetime, but you cannot have it. The reason is, if you have very low doping, then your base width modulation. So if you have low doping, then your depletion width will be higher, right? The higher the depletion width, then your neutral base width will be lower. So your base width modulation will be higher if you're low doping, right? In case of low doping, your base width modulation will be higher. Your early voltage, which is a figure of merit for your bipolar junction transistor, the early voltage will be low. And top of that, because you are applying reverse bias this junction is reverse bias, the collector base junction. So it may happen that if the doping is very low, so both the means your depletion width in the emitter base junction and the collector base junction may merge, right? So if they merge, that means your emitter base is shorted, right? So emitter collector is shorted, right? So that means very high current. So we call it punch through, right? Your punch through. So you means basically your um, I mean your transistor will enter the punch through region. Punch through means your collector based depletion region and emitter based depletion region is merged, right? That means we have a direct connection between emitter and collector, and there will be high current flow, right? And so we do not want that, right? So do not want that. Then we want our NB to be high, right? Generally, we want our base doping to be high, right? Because to avoid base width modulation and the constant effect, we want our base doping to be high. But we cannot have our base doping high because the moment you increase the base doping, you will have your means your lifetime, the recombination lifetime will be affected, right? So these are a lot of trade-offs, right? So you have to really see means when you're designing a bipolar junction transistor, you have to take care of all these effects together, right? Okay. So means we are using means in 1980s, right? So when 1970s, 1980s, when bipolar junction transistor was very famous, right? Because most of the circuits are made using BJTs, right? So that time people are using silicon BJTs, right? But then people found something about heterojunctions, right? So heterojunction, heterojunction idea is there in 1950s and 60s, but it came into picture in 1980s, right? So from Germany, so a scientist from Stuttgart actually, so he proposed, he actually showed, right, by fabrication, he showed the advantage of heterojunction, and he got the Nobel Prize, right? So the Kroner, right? So Kromer, right? So he got the Nobel Prize for discovering the heterojunction and utilizing it, right? So idea behind heterojunction, I mean, when we talked about heterojunctions are now used everywhere, right? So like one is bipolar junction transistor, but if you think about photodetectors, lasers, or all those optoelectronic devices, right? The heterojunctions are heavily used, right? Um, uh, so talking about heterojunction, so if let's say band gap, right? If my band gap of emitter, right, the emitter is more than band gap of base, right? So this is where, because if the band gap of emitter is more than band gap of base, right? Let's say, then NIE, because your band gap has inversely proportional, or your intrinsic carrier concentration is inversely proportional to band gap, right? So this will naturally happen, right? Right. So your intrinsic carrier concentration in emitter will be lower than intrinsic carrier concentration in the base, right? If it happens, right, if you go back to our equations, right, here, right, IP, right, so we told, okay, we want our NIE to be low, right, and uh, IN, see, if you look at this equation, right, these first two equations, IN and IP, I want my IN to be high, I want my IP to be low, right? So if you look at the NI here, this is natural, right? So if I want to make a heterojunction transistor, I want my best material have lower band gap than the emitter material, right? Because I want NIE to be less than NIB. So this is what happened, and there are a lot of, a lot of devices. So if I give example, um, right? So we have 3 5 BJTs, or we call it heterojunction transistor, heterojunction bipolar transistor, HBT. HBT stands for heterojunction bipolar transistor, right? So this is heterojunction because, right, and this is bipolar, and this is transistor, right? So this is HBT, HB and T. So right, so we started having, means you could see indium phosphide and InGaAs, right? Indium gallium arsenide BJTs, right? Not BJTs, HBTs. So people started using this, and we have also silicon germanium HBTs, right? So these are very common HBTs. So heterojunction, right? So the common thing is, even if we use different materials and we have different type of HBTs, but the common thing is your emitter semiconductor material has higher band gap than the base semiconductor material, right? When you talk about indium phosphide, right? When you talk about indium phosphide here, so indium phosphide has a band gap of 1.3 electron volt, right? And indium gas has a this has a band gap of 0.75 electron volt, right? Similarly, when you talk about silicon germanium, this has a 1.12 electron volt, and this silicon germanium, depending on the concentration of silicon and germanium, so this varies between zero point 0.7 and 1 electron volt, right? So silicon germanium band gap, it could vary because we have uh, silicon 1 minus x and germanium x. So if your germanium percentage is 100%, then your band gap will be 0.7 electron volt, right? If your germanium concentration is low, then it will be very close to 1 electron volt, right? So you could vary the silicon germanium. So silicon germanium case, we talk about 0.7 to 1 electron volt kind of band gap. Okay, so so this is the basic concept. So what happens is, if you see, I mean, uh, we also discussed yesterday. I'll just copy these slides. I do not want to go. Right. So let me select this slide. Okay. So yesterday we talked about. So what we're talking about here is, you. so heterojunction in the case, right? So in simpler way you could explain is, so I have silicon collector, right? So I have um, here I could think of, let's say, silicon germanium base, right? And this is silicon emitter, right? So this is heterojunction, right? So my collector is made of silicon, my base is made of silicon germanium, my emitter is made of silicon, right? Or in the worst case, let's say I take this example, so my base is made of germanium and my emitter is made of silicon, right? So this is heterojunction, right? And this, so how to fabricate this cannot be fabricated in normal way, right? So what we're typically doing, when you have a homojunction, let's say I have emitter, I mean collector, base and emitter, I just create this, because this is n type and this is p type, this is n type for npn transistor. I create all those layers by doping, implantation, right? So I take silicon, then I implant collector, then implant base, then implant emitter, right? So I do it by implantation, right? But since I have different materials here, right? So I have to deposit, right? So I take silicon, then I deposit base on top of that, then I deposit emitter on top of that, right? So this is done by mostly by deposition. We don't call it deposition, we call it epitaxy, right? Epitaxy is when you will do crystalline material on top of each other, right? And epitaxy is a very popular process, widely used process, right? Epitaxy, silicon epitaxy, or right? So here we take silicon, then you deposit germanium, and on top of that you deposit emitter, I mean silicon again. So if so, we have also looked at this, right? So if you draw the band diagram, because if you take a heterostructure, let's say you take n-type silicon and p-type germanium, and you draw the band graph, your your band diagram. So your band diagram will look like this, right? So this is your band diagram. So your band diagram, right? So this is your band diagram. So if you see, since you have a different band gap material, right? So you will see your conduction band offset and valence band offset for your emitter based junction is different, right? So since your valence band offset, right? So your valence band offset is different than the conduction band offset. So definitely you will have asymmetric injection, right? So when you are talking about electron injection from emitter to base, that happens over the conduction band. When you are talking about hole injection from base to emitter, that happens over the valence band, right? So since your valence band offset and conduction band offset, right, or BBI you are talking here, is different, right? So that means in this case, your there it is easy for the electron injection, but it is difficult for the hole injection. So if since it is difficult for hole injection, so automatically your IP, the hole component, will be lower than the electron component, right? In the emitter current, right? And here, so this is one thing. So so if you do that, your IP will be less than IN, because you have your valence band, your key QVBI in the valence band is greater than QVBI in the conduction band, right? Right. So since they are different, and okay, so you could also means basically this difference you could so this is nothing but your band gap difference, right? So if you see what is the difference between QVBI C and QVBI B, so basically that will depend on your band gap, right? So if your base material has much lower band gap than electron, sorry, emitter material, then you'll have means asymmetric, more asymmetric uh, BBI, right? Most more asymmetric barriers, right? Okay, so okay, now the advantage of this, right? So if you look at the advantage, right? So we have done two things, right? So we have reduced IP because of this band gap difference or the barrier difference. We have reduced IP, right? But now my the electrons injected from E to B, the electrons injected from E to B Questions here? So your electrons injected from E to B is nothing but Ni base square, right, divided by the base doping, right, exponential Vb by Vt minus 1, right. So here my NIB is increased, right? So if you see, NIB is increased because your base has a lower band gap. Base has a lower band gap. So NIB has increased. So your NIB is increased, right? So NIB, let's say if you go to silicon to germanium, right, your NIB will be increased 10 to 6 times, right? So that means you are now injecting at the same VB, same base to emitter voltage, you are injecting 10 to the 6 more electrons from emitter to base, right? So this is a huge number, right? 10 to 6 means it's a huge number, right? But you don't want, if you don't want that huge number, like you current to increase by that much, so what you could do, I mean, basically you could at the same time you could increase your NB, right? So let's say you increase your NB by, it was previously around 10 to the power 17 or less, so now you could increase it to 10 to 19, right? So you increase your NB by 10 to 2 times, right? So if you increase your NB by 10 to 2 times, still you are getting 10 to the 4 benefit, right? So you are getting 10 to the 4 benefit. But now what you have done, you have increased your base doping, right? So since you have increased your base doping, right? Right? Your base doping has increased. So your base doping has increased means your base width modulation will reduce, right? Your base width modulation will reduce, right? And your early voltage will increase, right? So another way you could think, if your base doping has increased, right? So you could also reduce your because your base doping has increased. That means your depletion width, because your depletion width means emitter base junction, collector base junction has reduced, right? This part and this part has reduced. So you could scale now, right? You don't have to worry about bounce through. You don't have to worry about base width modulation. So you could reduce your base width, right? So your base width is reduced. Base width reduced means your transit time is also reduced, right? So um, um, these are some of the updates, right? So some of the advantages, right? So when we move from if you go to a lower band gap material, so lower band gap material helps you, enables you to increase the base doping. The moment you increase the base doping, you reduce your base width modulation, you increase your early voltage, right? So a heterojunction bipolar transistor HBTs have much higher early voltage than your typical bipolar junction transistor, right? And also, since your base doping has increased, right, you could make the base thinner, right? The moment you make the base thinner, your base transit time reduces. So base transit time reduces will help you in a lot of things, right? Yesterday in last class or last to last class we discussed about transit frequency, right? FT, right? If your base transit time is reducing, that means your FT, your transit frequency will increase. Transit frequency increases means you could operate your transistor at high frequency, right? So that's the reason HBTs means mostly when you're talking about terahertz kind of application, right? Terahertz means your circuits operating in terahertz, right? So definitely your CMOS transistor cannot support that kind of high frequency. So people are using HBTs, right? HBTs are widely used in terahertz applications, right? Right. So these are few benefits, right? Okay. Um, any questions here? Let me see. Nishant, Swati.
No, sir.
No, sir.
Okay. All right. So if there is no questions, so good. I hope you, I mean, you understood. All of you understood well. Um, okay. So Okay, let me go to the, I think, right. Um, okay, so let me go to the typical structure of a silicon germanium HBT. Okay, before going to the silicon germanium HBT, um, so here, see, another thing which I means another thing which is very important. I forgot to mention, that is base resistance, right? So we talked about intrinsic device and extrinsic device, right? So if you remember, so I have my emitter. So let's say I emitter, then I have my base, then I have my collector, right? But the contacts are on the top, right? Contacts, the emitter base collector contacts at the top, right? This is my intrinsic device, right? This is my intrinsic device, right? So this is my intrinsic device. But the electrons injected basically, right? Electrons injected, so they are collected and they are flowing to the contact, right? Like this, right? So this part here, right? So if I look at, so this is my intrinsic part, right? This is my intrinsic part. So other part is the extrinsic part, right? Other parts just add some resistance to the current flow path, right? So here, since this is the base part, so I have a base resistance coming into picture here, because this is the base resistance and this is my so I'll have also, so this is my base resistance and I'll have also collector resistance. So since I could increase the base doping, when you go to very means not very low band gap material in the base, we could increase the base doping. Since the base doping has increased, this resistance will also decrease, right? And resistance has effect on the high frequency operation, right? So when you talk about ft, the transit frequency, but when you talk about maximum oscillation frequency, f max, right? So f max heavily depends on the base resistance, right? So in the parasitics, mostly the parasitics, and these resistances are parasitic resistances, right? We do not want in the device operation. So base resistance also helps in the reducing the parasitics, right? So also means, because see, when we're designing also, right, we do not want your base resistance to come into picture. And also we saw here in the saw here, right, your base width can also be reduced, your base thickness can also be reduced, right? Right. But the moment you reduce this base thickness, right, so you reduce this base thickness, right, so your resistance depend on the base thickness, right? So because you reducing the base thickness, the reduction of base thickness will improve the transit time, base transit time, right? The moment you reduce the base transit time, your RB, your base resistance will increase, because your cross sectional area for the whole flow is cross sectional area is reducing, right? So that will also increase your RB, right? So what I'm telling, if you are reducing your TB, that means you're increasing the transit time. Sorry, you are reducing the transit time, but your base resistance is increasing, right? Base resistance is increasing, right? So we do not want that, right? You don't want your base RB to increase. So if you don't want your base resistance to increase, what is typically done? So we have, since we discussed about polysilicon emitter, right? So we discussed about polysilicon emitter. So we use emitter, we deposit emitter, so that we want higher emitter thickness to manage the current emitter, whole component of the emitter current. But also to take care of the resistance, we have a base. We also deposit base poly. So what is done is your base thickness is reducing, right? But intrinsic base thickness is reducing. But you do not want your extrinsic part, right? Extrinsic part of the transistor, you do not want your base thickness to reduce, because extrinsic part, if you reduce your base thickness, your base resistance will increase. So that is avoided by depositing a polysilicon base, right? And this process is called double polysilicon emitter BJTs, right? Emitter, BJTs. And when we're talking about heterojunction transistors, right? Heterojunction transistor always comes with a double polysilicon, right? Double polysilicon, because your emitter is also made of polysilicon, your base is also made of polysilicon. So when you're talking about this emitter and base polysilicon, that's the extrinsic part of your, right? It is not this is not influence or intrinsic operation. So your base polysilicon part is mostly done to reduce the base resistance. Okay, so when you go to the structure of a typical silicon germanium HBT, so we have 15 more
Sir,
minutes. Yeah,
sir, in the polysilicon base, that will be the outside part, right? Similar to the in the
that
polysilicon
will be in the
emitter.
outside. Yeah, I'll show that in the structure. Huh.
Uh,
Sir, can you,
yeah, go ahead.
Yeah, Monica.
sir, can you please tell, like, if the transit time is decreasing, why is the resistance of the base increasing? Because it is like the flow, the electron will have like it will flow easily.
No,
So
no,
we have.
no. This is the extrinsic part, right? Huh. See, this is the extrinsic part, right? Resistance is not coming in the intrinsic device, right? So this is good because see, because your whole, if you understand the extrinsic part, so because your contact is at the top, right?
Yes, sir.
Right. So we have my emitter here. I have my base, right? Okay, this part is your transistor. Your base thickness means your electrons injected, then they could easily flow to the collector, right?
Yes, sir.
But the holes are coming from this side, right? Right. So you are applying your base voltage here, right? And there is this part which is the extrinsic part, which is not taking part in the device operation, but it has a finite resistance, and that resistance, because then your actual voltage reaching the junction is VB. We have done that, right? IB times RB, right?
Yes, sir.
Right. And this RB, it depends on the thickness of this region here, right? So if you're scaling, if you're reducing this down, you're reducing this thickness down, that means your RB will also increase, right?
Yes, sir.
Right. And don't mix the extrinsic part and the intrinsic part. Intrinsic part, anyway, we want our base thickness to be low, right? But the secondary effect that we are having, that moment you make the base thickness lower, your RB increases, right? RB, your base resistance increases, right?
Yes, yes. Understood, sir.
Okay. Okay, so that's the reason. I don't want to increase my base thickness. So what I do, I have a polysilicon part here, right? So my extrinsic, even if this thickness is reduced, right? But I have externally, I have I made my base extrinsic part made of polysilicon. So polysilicon part I could highly heavily dope it, and I could do a lot of things so that your RB overall your extrinsic base resistance reduces. So here, so okay, so this is the structure of a typical silicon germanium HBT. Um, okay, so here if you see, I don't know, you just I'm just zooming this part. So here this is your emitter, right? So this is your emitter, right? This is emitter poly, right? Okay. So and this part is your base, right? This part is your base, right? This is silicon germanium in this case, silicon germanium base, right? And here if you see, this is my extrinsic base here. Sorry, yeah, this is, I mean, let me, this is my extrinsic base, right? And here this one my base poly, right? This is my base poly, right? So if you look at the base, this green yellow, sorry, not yellow part is emitter, this blue part is base. So your device part is, this one is your device part, right? So basically you're not talking about your device, this is your device, right? So this is emitter, base and collector, right? But outside this, the intrinsic part, right? So this is the extrinsic part. The extrinsic part, I want to minimize the extrinsic part, right? So to minimize the resistance here, I have this base, polysilicon base, right? And polysilicon base and polysilicon emitter is separated by a spacer, right? This region here, you see this region here, this is made of nitride, right? This is nitride insulate, right? So this is a separating, because I don't want my emitter base contact to be sorted. So right. Okay, so and you see, and the collector, when we're talking about electrons are injected, but electrons are going through all these things and collected here, right? So this part is also contributing to a resistance, right? Right, right. So that's the reason I made my collector. This is called the buried collector part, and my buried collector, you see the buried part, right? This part is buried here, right? This part, right? This is the buried collector I call, and this buried collector is made of highly doped N plus, so that RC, the extrinsic collector resistance, is low, right? And but my actual collector part is here. The collector, actual collector is here. Maybe I put, right. Actual collector is here. Sorry, this part here, right? So if you see your collector base junction, this part can be low dope, right? So this part here, this part can be low doped, right? Right? This part could be low dope, and when doping of a collector decides your breakdown voltage, right? If you want to operate at higher VCC, you have to make sure that your VBCBO, and VBCBO is nothing but this junction, right? Your VBCBO is this junction, right? This junction breakdown voltage. You want this, if you want this junction breakdown voltage to be low, or sorry, high, right? Then you have to actually, means you could change your collector doping, right? Collector doping is mostly managed to manage the VBCBO and VBCO, right? Right. So this is the typical HBT. So if you see, uh, you have this trench isolation, means a deep trench isolation. So deep trench isolation just isolate. So this is isolates one BJT from the other BJT in the die, in your silicon wafer. This is self-alignment process. I will not go there because you have double polysilicon layer. The self-alignment process is used. Fabrication. We will not discuss the fabrication flow of a polysilicon emitter BJT. The collector implantation is selective in the sense that based on your requirement, right? Whether you want higher BVCBO or lower BVCBO, so based on requirement, you could implant your collector. The silicon germanium base is obtained with epitaxy. So as I told, so you have to deposit. So you deposit, you have your collector, then on top of that you deposit your base, on top of that you deposit your emitter, right? Okay, and here actually the emitter, when you actually fabricate, right, in the real process, what you do is you have your collector, right? You deposit silicon germanium base. So this is silicon, this is silicon germanium base, this is silicon collector. So before you do silicon, because you have your emitter is made of polysilicon. So before you go to polysilicon, basically what you do is you have a very thin silicon cap, right? That is done by the epitaxy, right? This silicon cap, silicon emitter, and top of that you do the polysilicon, right? Right. So this whole part, the emitter has a polycrystalline part and the single crystalline part, right? Right. So so and your base has silicon germanium and your collector is made of silicon, right? So but this is done for some reason, and I don't want to go there because this will take a lot of time, right? We are not going very deep into fabrication process of silicon germanium HBTs, right? Okay. So this is a typical HBT that means the TM cross section. So this is taken from IBM. Actually, I have taken these slides from Thomas Zimmer, University of Bordeaux, because he was giving. I mean, actually, he presented about HBTs in one of the meetings in India. So I have taken his slides. So here you see, if you, this is the cross section, right? This is just fabricated device. They have taken the cross section. and you could see this is your collector, right? So this is your collector. So this is your emitter. This is your base. But you see, this is your buried collector, right? Right, buried collector part, right? And your emitter polysilicon. This is your emitter polysilicon, right? And you have your base poly, and this is your base polysilicon, right? Base contact, right? And your somewhere your base is somewhere here, right? Very, it is not shown here, right? Your base is somewhere here. You cannot really see, right? And base is contracted, intrinsic base is contracted through polysilicon, right? And it goes to the contact, right? And this doping of this polysilicon layer right here, right? Doping and thickness of this polysilicon layer determines the base resistance, right? And similarly, the doping of the buried collector layer here, right? Buried collector, that determines the collector resistance, right? And you have your emitter. Okay, and these are the deep trenches, very deep trenches to isolate different bipolar transistors on the chip, right? On the IC. Okay, and if you look at the doping profile, right, it's very interesting. So, so before going there, right, let me put something, right. So, okay, so let's say I have my emitter, base, and collector, right? So, if my base, once we talked about uniform doping. Let's say base is doped like this, right? The base doping is something like this, right? Um, right. So, I mean, okay, you could think of, right. Let's say instead of uniform, your base doping is your emitter is uniformly doped, right? Your collector is uniformly doped. Let's say your base doping is something like this, right? So it has a gradient doping. So it is high at the emitter base junction, it's low at the collector base junction. What will happen, right? If you draw the band diagram, how will it look like? Can you draw the energy band diagram with this, with a base doping which is varying from emitter base junction to collector base junction, right? So okay, so if you draw the energy band diagram, basically you will start with your Fermi level, right? And this is N type. So I have N type silicon. Let's say silicon. This is silicon, right? Um, right. This is highly doped, right? N type. Then I have a P type, right? So you see, you have a graded doping, right? So your doping, your Fermi level is flat anyway. So right, your Fermi level is flat, but your base doping is changing. So base doping is changing from emitter base to collector base. So if you look at the base, right, so you'll have something like this, right? So you could have something like this, right? So right, so you see your emitter base junction has higher doping, so conduction band, valence band will be close to EF, and but far away your valence band will be not be close to EF, right? So now if you draw right, and this will be your that's when then your silicon again. So your collector, so collector is not highly doped. So it will be something like this. So if you connect, so basically you will have something like this, right? So means I cannot do it properly, but you could properly do. Right? Let's say it has a band diagram like this, right? So if it is a band diagram like this, so what will happen, right? So what will happen? Hmm? So see, you look at the base, right? If you look at the base, right? If you look at the base here, will there be electric field in the base? Anybody?
Electric field will not be on the emitter side.
No, I'm talking about base region. Will there be electric field in the base?
No, sir. Not on the left side there won't be, but on the right side junction there will be.
No, see, there is a energy change from left to right, right?
Yes, sir. There will be electric field.
Okay, so there will be electric field, right? Since there is energy,
Yes, sir.
in energy band diagram, look at the energy, conduction band energy, it's not flat, right? Then there is a slope. That means
Yes, sir.
there will be electric field. And what is the direction of that electric field?
So from left to right.
From left to right.
Yes, so from emitter base to junction to the collector base junction.
From right to left, it will be.
It will be from right to left, right? Yeah, you think about it, right? It will be right to left, right? Okay, the electric field, right? So you see, now means I have an electric field in the base, right? So the moment the electrons are injected, the electrons will diffuse there will be diffusion because there is a concentration gradient from emitter base junction to collector base junction. On top of that, I have a field which is also yielding, means aiding, means which are also helping the electrons to go from emitter base junction to collector base junction. So in this case, the movement or transport of electrons from emitter base junction to collector base junction is not only because of diffusion, it is because of diffusion plus drift, right? Right. And since there is some drift component, that means electrons are moving faster, right? It was moving by diffusion, but since there is a drift component which is helping the electron movement, it will also move faster, right? So if I have a slope like this, doping slope, my transit time will reduce, right? So that is the advantage, right? So but how to create this kind of profile? It's very difficult, right? If I means precisely by I could not do that. Otherwise, if I could do that kind of base doping profile, if you see that my transit time will increase, transit time will reduce, and that will help increasing your FT, right? And beta also, because transit time is reduced, means transit time is reduced means your electrons are spending less time in the base, so the base recombination current will be low and your IB will be low and your beta will increase, right? So this technique actually they used in the silicon germanium. Since silicon germanium, what they did is, so the germanium concentration. So when you deposit, right? So let's say you have collector and you have base and you have emitter, right? When you're depositing, right? When you're depositing base, right? I told this is silicon germanium, right? So they have increased the germanium concentration, right? Silicon germanium. So if you see, if I have uh, this this material is not uniform. This is a graded material, right? That means if I have silicon 1 minus x GX, right, and I have increased this value of x from this side to this side, I have increased the value of x. That means I have increased the value of germanium content, right? So that can be easily done during deposition, right? When I'm depositing by epitaxy, right? So I could easily manage the concentration of germanium from collector base junction to emitter base junction, right? So in this case, if I do that, right? If I do that, that means if I think of a base, if you think of a base, right? You have collector, you have base, and you have emitter, base, and collector. So here I have higher germanium concentration. So the band gap, I have a graded band gap, right? So your band gap, basically, if you look from, if you go from top, sorry, if you go from bottom to top, your band gap is increasing, right? Because I have higher germanium concentration here, right? If I see silicon 1 minus x germanium x, my x is higher here. That means my band gap is lower here, and x is lower here, right? I have a graded concentration, right? When I'm depositing, I have a graded concentration, right? That means my band gap is increasing from collector base junction to emitter base junction, right? So if that is the case, right? If I draw the band diagram, means you'll have right. So I have my emitter, right? And my collector also. Let's say this is my collector. But my base has a graded doping, right? So since my base has a graded doping, so I'll have base something like this, right? So my base will have a graded doping, so it will um, decrease, right? So I'll have a slope like this, right? Because here my germanium concentration is high, and here my germanium concentration is low. So I'm going from higher band gap to lower band gap metal. That is very easy to do while deposition. I could control my germanium concentration. So if I do that, then I'll have, let's connect it, right? So right, what will happen? I have a automatically I'm creating an electric field, right? And it will also reduce the transit time and increase the FT, right? This technique is used in HBTs, right? Um, so this technique is used in heterojunction bipolar transistor. So that's what it's shown here, right? So you see your germanium, there is a germanium profile. As you're telling, this is how the HBT doping profile looks like. So I have emitter which is heavily doped, right? And emitter has two components. One is polysilicon emitter. This part is your polysilicon emitter, and this is monocrystalline single crystalline emitter. Then I have base. There is a base doping which is graded, as well as on top of that, my germanium profile is also graded. And then my collector, right? I have a buried collector, and this part is your collector which controls your background voltage. And this is my buried collector which is highly doped to reduce, right? Like this part, right? You see here, right? Um, and you could see here, right? This is the highly doped collector part, right? So this buried collector part, right? Highly doped, this part here, right? This part, right? Okay. So this is a typical HBT, right? And they call it trapezoidal germanium profile, because germanium profile increases from emitter base junction to collector base junction, and it improves the transit time. It actually reduces the transit time and increases the FT. Okay, so I think I mostly have mostly done, and because to control the base, because base is p type, and p type diffuse faster. We don't want our base width to be very high, right? So they put means carbon is used, and carbon actually controls the diffusion of base, right? And okay, so the last few slides, if you see, there are a lot of companies are working on high heterojunction bipolar transistors. So there are few named here, like in Europe, Infineon, ST Microelectronics, IHP, Global Foundries, NXP, TI. So many means, because as I told you, right, heterojunction bipolar transistors, they could operate at very high frequencies, right? And silicon CMOS, we'll discuss about MOS transistors starting next class, but CMOS technology cannot be used at very high frequency, right? So that is the reason when you're talking about terahertz application or very high frequency applications, right? So you use HBT technology. Mostly they're called BiCMOS, because you have a CMOS process. You have a process where you have both MOS transistor as well as bipolar junction transistors, right? We call it BiCMOS process, right? So this is the bipolar CMOS process. That means we have both bipolar transistors and MOS transistors in the same technology, right? And you see, if I look at the what has been achieved by now, right? So you have HBTs working at 800 gigahertz Fmax, right? And maximum frequency or FT, right? around 500 gigahertz, 800 gigahertz. So basically, this is the frequency because CMOS, MOS transistor cannot operate at that frequency, right? Right. The transit frequency of bipolar transistors, people have achieved almost 500 gigahertz. So now means this is a old slide, 2016 slide, but people have already gone up to 1 terahertz kind of FTF max, right? So almost reached terahertz frequencies, right? So that means your transit frequency is almost 800, 900 gigahertz, 1000 gigahertz, right? Yeah, so this is only possible because of advancement, means how to design your bipolar junction transistor, right? How to design your base region, how to design your collector region, and how to design your emitter region, right? So um, I'll just keep it. You see, this is a typical cross section of HBT. You see, you have emitter, right? You have silicon germanium. This is base, and this is my collector, right? So you see, this is the base region, the intrinsic part of the base, extrinsic part of the base, extrinsic part of the base, right? Um, okay, and this is a typically the cross section of a full IC, right? So you could see front end, back end. So here you see CMOS is integrated. Means if you look down, so mostly your bipolar transistor, your MOS transistor is here, and see here this is your MOS transistor, and you could see your BJT is this part, right? Right. So you have technologies where you have MOS transistors integrated with your high frequency bipolar transistor. We call it BiCMOS process, right? Yeah. So BiCMOS processes are very common nowadays. Mostly for high frequency applications. Right? People do not use bipolar technologies for low frequency applications because they are expensive, right? Much more expensive than CMOS process, right? Because you have epitaxy. The moment you use epitaxy, your cost increases, right? Because it's a very slow process. Okay, so I think I'll stop here today. So we have finished bipolar junction transistors. So if you need more information, all those information you could find in the research papers, books. Means not all books, maybe very standard. Means if you go to advanced books, you'll find all those information. Um, okay, so I think you could do that. If you have any doubt, you could talk to me. You could talk to the TS. Uh, but read books, right? I'll share these slides, but with the slides also, please read books.